All right. Please bear with me as my throat and speech comes back from that nasty flu that I got like a million years ago. So good night, good evening, and welcome to tonight's segment of the Faculty Lecture Series. If you don't know who I am Jessica Lardy. I'm professor and director, and I coordinate the series. So thanks for attending tonight's lecture. Keep an eye out for upcoming lectures. There's rack cards over there for the remainder of the schedule. Next week on Wednesday, we'll have a lecture featuring Professor Olivia St. Ange from the School of Business, and next Thursday, we'll have another lecture featuring Professor Brittany Harlan and Dr. Kyle Glenn from the School of Business. So this evening's event is presented by Dr. Choyan Lahiri of Geosciences in the School of Science, Technology, Engineering, and Mathematics. Dr. Lahiri is an associate professor of geosciences. He earned his undergraduate degree in geology from the University of Calcutta, a master's degree from the University of Idaho, and his PhD from the University of Mississippi. Dr. Lahiri was born and raised in Kolkata, India, moved to the U.S. in 2006 for graduate school. He loves to eat and cook, read, teach, hike, and take pictures of geological features. And also he loves dogs, of which will be featured tonight. Tonight's lecture is titled, What is GIS? An Introduction to GIS and its Applications in Environmental, Social Sciences, and Business Administration. And in his words, Geographic Information Systems, or GIS, have emerged as an indispensable tool for analyzing and visualizing spatial data across various disciplines. At its core, GIS integrates hardware, software, and data to capture, manage, analyze, and display geographically referenced information, enabling users to identify patterns, relationships, and trends in space and time. This lecture explores the foundational principles of GIS and its transformative applications in environmental sciences, the social sciences, and business administration. So help me in welcoming Dr. Lahiri.
Thank you, Jess. Thank you for coming to this evening's talk. My talk is going to focus on this question of what is GIS and what are its applications in various fields, some of the things that Jess mentioned. Before I start, I would like to do two things. I would like to go to my acknowledgement section and acknowledge some people and some things. First of all, I would like to acknowledge the contribution of my parents and family in my life. Without their help, their support, their love, I wouldn't be here. So thank you to them. I would like to also thank my colleagues, Tim Deal and Liz Heal from the U.S. Geological Survey, and my students. And I'm doing that for two reasons. Number one, through these associations, since 2019, I've learned a lot and grown as a professional. And these experiences are things that I've been able to bring into my teaching, and my teaching has been enriched considerably using some of these experiences since 2019. I would also like to a special thanks to Richard Hubler and Deacon Aspinwall. They contributed an example that I'll be sharing with you shortly. And I would also like to acknowledge the data resources that I'm using or will be using in this presentation. These are all free data resources. You can download as much as you want, as many times as you want. And they're all available on the internet. If you need any help with any of these data resources, I'll be happy to chat with you at some point. Before we get to the outline, what I would like to do is open it up to the audience and see what experience, if any, and Doug is not allowed to answer this question, what experience, if any, you have with GIS. Anyone? Paul?
excuse me, looking at different data about the San Luis Valley in terms of population density, socioeconomic variability that's been mapped to different parts of our community.
Okay, Eliza?
Well, I took your class last semester, but like landslide hazards for towns, mountain towns, and stuff like that as well, like different hazards.
Okay, anyone else? All right, so the reason why I asked this is hopefully by the end of this talk, I'm hoping that we'll make an improvement in your understanding. Hopefully you learned something today and I can get you interested in GIS, and maybe you'll take a class in GIS shortly. So let's start with an outline. The first three things that we'll be focusing on, we'll look at a definition. We'll look at some data types. It's not going to be comprehensive. It's going to be a subset of the data that is available that you could use to do GIS. And then we'll look at some types of analysis. We'll look at two types. We won't have time to get into a lot. After that, we'll get into these 4 examples. Each of them are from 4 different states, and they will be tackling different aspects, different subjects. The Tennessee data set is the data set that I have the most experience with. The other data sets, the Mississippi and the Oregon data set, I downloaded a couple of weeks ago to create some examples, some basic analysis to add to this presentation, just so that I can show you some examples in the field of fields that I'm not familiar with. I don't work in these fields. So those two, the Mississippi data set and the Oregon data set, are things that I downloaded. The Colorado data set, like I mentioned, Richard Hubler and Deacon Aspinwall provided that data set to me. So I'll be sharing that with you shortly. Okay, so let's get to the definition. Before we get into a real definition, let's see what the acronym GIS stands for. So GIS stands for Geographic Information System. However, Dr. Benson, Rob Benson, used to say GIS means Guaranteed Income Source. And I'm really hoping that by the end of this talk, you will see that Dr. Benson was not only being funny, he was actually saying this thing based on reality. There is truth to the fact that GIS is a guaranteed income source. Now let's look at a definition. And this definition is provided by Esri. Esri is the company that produces the software ArcGIS Pro. And this definition is short, but it encompasses what is most important about GIS, the science of where. That's what is at the heart of GIS, because all the features on the Earth's surface, cities, rivers, forests, have a location associated with it. Where are these locations? That's what goes into the science of where. And not just where are these locations, but where are these with respect to each other? Where is the city located with respect to the forested areas or the river? Because that plays a very important role. If the city is by the river, it's easier to flood the river. If you have, on the other hand, a city next to a forested area and the river is next to it, then it would be less susceptible to flooding. So again, it's this question of where that goes into the science of GIS. Where are these features located? Let me give you another example. If you go to a city, for example, cities have more densely populated areas and less densely populated areas. So where are the more densely populated areas in a city? If we locate that and find out where a groundwater pollution plume is with respect to where the densely populated areas are, we would be able to plan and mitigate the situation better. So again, everything in this field goes back to that question of where. Where are these things located? Where are these features located? Where are these phenomenon located? How far did it flood in 2011? Where was the flooding? Where did the flooding end in 2011? Where did it go up to in 2019? Those are the questions that are very important in deciding or planning forward, doing analysis in this field. Let's look at a more descriptive definition. This is a definition by the US Geological Survey. And you'll notice that I've got 4 action words highlighted in red: to create, manage, analyze, and map. These are the actions that one performs when one is doing some GIS analysis. And we'll be getting into these action words in detail as we go through our examples. But for the time being, what we're going to start is looking at data that's available. What is the data that we can use to do GIS? So let's start with the oldest data sets. Here is a topographic map. This is a topographic map of Warfano County, and it's a map from 1889. Now, this map, and all maps, topographic maps that the USGS has produced up to 2006, fall into the category of historical topographic maps. The reason why that is the case is maps up to 2006 were printed and distributed as printed copies, and they were based on traditional cartographic techniques to be produced. They were produced using traditional cartographic techniques. Anything post 2006 are newer or modern maps. So this definitely falls into that category. And in fact, there is such a large body of literature about how mapping techniques have evolved, whether it's USGS literature or published in journal articles. I would love to do a talk at some point to show you some of the ways that the mapping techniques have evolved. So this, again, is a historical topographic map. And just for your reference, this is where the top of the Lovita Pass is. This is an aerial photograph. This is a historical aerial photograph. This is another data resource that you can use in GIS. This is a historical photo from 1953, October 10, 1953. The USGS, the BLM, the Forest Service, the US Department of Agriculture, all of these agencies have been collecting aerial photographs. I've seen an aerial photograph that goes back to 1930. So these photographs are very valuable additions to GIS analysis. I like to focus in on this section of the photograph just as a point of interest, because this is again the top of the Lovita Pass, and you'll notice that the highway, the new section of the highway, doesn't exist as yet. The highway turned at this point into the old section and entered into the valley. Here is a modern topographic map. Here you can of course see the highway. This is the new highway. This is missing here. The new highway, the new section was put in, I think, in 1963. This is another source of data that can be added into GIS analysis, a topographic map or topographic maps. In addition to this, one could create data from these resources. How could you do that? What I've done here is I've just traced over this map, and I've traced over drawn the ephemeral streams. I've drawn them out in dotted lines, and these are ephemeral streams in a section of the map. So I've created some data from a topographic map. You could do the same from a historical aerial photograph or a historical topographic map as well. In addition to creating lines, you could create points. Points could represent sampling locations, restaurants, houses. any of that data. Or you could draw polygons, just like I've drawn lines. You could draw polygons around property boundaries or the boundary of a study area. That's also a possibility. So you could create points, lines, or polygons from pre-existing data, that is maps or aerial photographs. Here is another example. I've just drawn over the new highway. That's an example of a line. So this is another example of how I've created data. Additionally, you could go out to the field, take a GPS unit and go out to the field and collect data, which you could use to create your points, lines, or polygons. Additionally, you could also, if we go back to this, I've already drawn these ephemeral streams and the highway. You could take a GPS unit out to the field, and if you identify a mistake in your map based on what you've drawn out, what the data that you've created, you could always modify and update the data that you've created. So with your GPS unit, the data that you're collecting, you could use that to update or modify the data. Because, for example, the road changes. A county road, there's a new bend in the road, which is not mapped in a version of the map. You can always go out to the field with your GPS and map out that section and make a change in your data set. So this is a way of collecting and modifying your data. And by the way, you're welcome to ask questions at any point. Please stop me if there's a question. I'm happy to answer questions if there's one during while I'm talking. Okay, so I'm sorry it's cut off, the scale is cut off at the very end. This is another example of data. This is a satellite image. Satellite imagery goes back to the 1970s. Landsat, the program Landsat, this is a particular type of satellite images. Nowadays you have a bunch of different platforms that you can download data from. This is a Landsat image. And just for your reference, this is the Sangre de Cristo mountain range. Alamos is located somewhere here, and that is the top of the Lovida Pass. One last type of data. This is LiDAR data, LiDAR imagery. It's actually a hillshade. LiDAR imagery that produces a bare earth surface. Now you'll see that this is Highway 160, and it's from this point, it's about a kilometer and a half to the top of the pass. And what is interesting to note here is that there are these two little landslides, this one here and this one here, that can be identified in this LiDAR data. I'm sure you guys have driven past this many, many times and not noticed it because of the vegetation that covers this area. If you hike up to these locations, you'll probably be able to see it. But otherwise, this is a good way of identifying some of these smaller features, especially in wooded, forested areas. Okay, so this is the end of the section on data. Again, wanted to remind you that this is just a subset of the data that you can use. And the fact that all of this data is free. This is all free data. Sometimes I find it hard to believe that all of this data is free. It's so expensive to collect all of this, but it's freely available. A couple of other things before we move forward. One thing is, please, please, please never trust the data without testing it, because data often has inaccuracies in them. So never take the data to be the truth. It's always a good idea to go into the data and check different locations to see if it's making sense or not. That's a very important thing to do. Geospatial data always, or many times, I shouldn't say always, but many times have inaccuracies that need to be checked out, number one. After you've done the analysis, which we're going to get into next, it's very important to ground truth what you have achieved in your analysis. Because this is not, the analysis that one does in GIS does not always represent what is happening on the ground. Some of the errors in the raw data might be carried over into your analysis, or the analysis itself might be wrong. there could be some errors in the analysis. So it's very important to, at the front end, check the data. The metadata, the data about the data is available with all the downloads. It's very important to go into the data, the metadata, check the metadata. And I'll go so far as to say sometimes there are inaccuracies even in the metadata, which I've found. So if you call one of these agencies, the agencies who've collected the data, they could confirm or give you the information that you're looking for. Okay, so let's then move forward to the types of analysis. What we're going to start with is an overlay analysis. So let's look at this square patch of land, and what I'm going to do is I'm going to add a grid for our reference, and I'm going to add these lines in which represent street data. So that's one layer. Let's add in another layer. This is the layer that shows urban areas, buildings. And then we've got the vegetation. So we put these three layers together and we get to our integrated layer. So we've got layers representing street, buildings, and vegetation. How can we do an overlay analysis with this? So we can ask the program, let's say we are interested to buy a house in this area. We can ask the program, find me the location of houses which are closest to the road and are also in a wooded area. Let's say I like being in the shade. So I can ask the program, tell me all the areas where there are lots of trees and it's also close to the road. This is just 2 layers of data. You could add more. You could have like water bodies, let's say, or grocery stores in separate layers, and ask the program to query, include those layers in your query as well. So again, these are individual layers that you've stacked and created an overlay, and you're asking the question, querying to get to a particular answer. One thing to note here is that these layers are representing the same unit of time. They're not representing different time periods. All of these, the street, the position of the street, the length of the street, the building, location of the buildings, and the trees are all at the same time. It's a snapshot in time where you're asking the program, can you tell me where the best location is for my house, depending on what I need. Now, what we're going to do next is we're going to look at another type of analysis where we're also going to overlay data, but in this case, we're going to have data sets that are recorded at different time periods. This is a Sentinel-2 image. Sentinel is another satellite image, and this is showing you the Highway 160. That's the new highway, and this is the old highway, just for your reference. And you can see that this image has 2 colors. Bare rock and soil, the grayish color, and you've got the green, which is the vegetation, grass, etc. This is recorded in 2017. Let's go some years forward, and this is 2023. So again, this is the road. What difference do you see?
Not nearly as much vegetation.
So there's a huge reduction in the vegetation. So in this case, what we could do is we could overlay these different time periods and analyze how much has the vegetation changed. Where is the change the most? Those are the questions that we could answer. We're still overlaying, but as opposed to the previous example, in this case, the layers are not at the same time. They are different. They are representing different time periods. So it's more like a time series analysis. You're looking at how different is the landscape, how has it evolved over time. Okay, so now that we have covered the types of analysis, now let's get into the first example, which is from Mississippi. This is a base map that I got from ArcGIS Pro. It has the 2 very important elements that a map should have, a north arrow and a scale. And you'll see that it has the base map has the water bodies, the little towns, the highways, and it also has the boundary of the county. This is Humphreys County in south central Mississippi. And what we're going to do is we're going to add layers. This is an example of an overlay that we're going to do. We're going to add layers. So we've got the county boundary, we've got the highways, the water bodies, the larger towns are in yellow, and we've got the smaller towns in the red circles. And now what we've done is we've been able to create a map using all that data. So we've got a legend as well, and this is a map that's very usable. So one of the things that I said GIS can do is it can map data. So this is an example of what you could do with GIS. Before I go forward, I would like to ask you, why did I add all of this data? Because I've got this base map which already has the data. Why did I take the trouble of adding all of this up? I could have just done I already had the scale and the north arrow, rather the scale and the north arrow, and I could just have added in the legend. Why did I add all of this data? I could have just used the base map.
It makes things a whole lot more visible.
That's one. Visualization, definitely one.
Shows relationships, like you're able to see size of towns better.
Yeah, that's also very true. Yeah, that is absolutely true. So visualization is improved. Anything else?
The water bodies very detailed.
Yeah, they're detailed. There's one thing that I was trying to tease out. You
Go back to the base map.
sure? Yes, the county is better delineated when you add the layer. The thing that you can achieve by adding in this data is that you can do analysis on it. The base map is just an image. There's no way that you can do anything. You cannot manipulate anything in here. This is fixed. This data can be manipulated. So in addition to everything that you guys said about better visualization, better, you can see the cities better, the bigger cities better than the smaller towns. That's all true, but it's also true that this data can be manipulated. So let's look at an example of data manipulation. So I'm going to ask the program, group the larger and the smaller water bodies and color code them in 2 shades of blue. And I'm going to just use an arbitrary number of 1 square kilometer. Anything that's 1 square kilometer or larger is going to be the larger water body, and anything smaller than that would be smaller water bodies. So here is our final map. Let's add in the data. So now we've got the darker shades of blue showing you the larger water bodies. The lighter shade of blue is where you have, those are catfish ponds, by the way. So those are indicating your larger and smaller water bodies. Let's do another example. I'm going to ask the program to delineate all the urban areas which are susceptible to flooding. And again, the query that I'm going to use here is water bodies that are closer than 300 meters. Anything that's closer than 300 meters to a town, deem those to be susceptible to flooding. And I'm not saying that that is the criteria which floods towns. I'm just using that as a query, just as an example. So again, this is our, incidentally, sorry, I misspoke. I'm going to ask, the query was going to be which of the towns are 300 meters, closer than 300 meters to the larger water bodies. That is what my query was. Sorry, I misspoke. So again, this is our where we were earlier, and now what I've done is I've got my larger water bodies in dark blue, and light blue is where I have the smaller water bodies, and you'll see that the towns that could flood are in pink. All these are in pink, except for these yellow dots, which according to the query don't fall within 300 meters of a larger water body. So what we've achieved here is we've done an overlay analysis and we've answered some basic questions about the proximity to water or the size of the water bodies. Incidentally, my connection to this area is this is Sky Lake. Sky Lake is where I did my dissertation, and I always went to collect data on Thursday or Saturday because about 50 miles north of here there's a all-you-can-eat catfish buffet called Larry's Fish House, which I love to go to. So I always made sure to collect data on Saturday because they're only open for lunch and dinner on Thursday and Saturday. Okay, so this is our first example. Let's just go back to the definition that we started with, the more descriptive definition, and see what can we identify what we've done so far, which of the action words we've covered so far. Have we created data? Yes, we have created data. We've created a subset. That's definitely, we have created data. How about the others? We have not, now I must say that management of data is something where you save, store, update. Those are the things that are associated with management of the data. We haven't done that in the examples. However, I did talk about taking out a GPS unit to the field and updating layers. That's one way of management. But other than that, we're not going to get into this action word anymore in the course of this presentation. Have we analyzed and mapped? We definitely have done some very basic analysis. Okay, and what types of data have we used so far?
We've used like highway systems, marked down little towns and bigger, like urbanized towns.
Yes? So we've used lines, points, and polygons to represent what you just said. Okay, so let's move on to the Oregon data set. This is a little more complicated than the first one, and we're going to look at some different applications here. This is the state of Oregon with the counties delineated, showing you the names as well. And this data set, the data set that I just showed you, this has a lot of information in it. We've got demographic information, socioeconomic data, agricultural data. So what we're going to do is we're going to start with the population data, and we're going to throw in another data set, which is the location of volcanoes with the number of eruptions that each volcano has had. And we're going to produce a basic volcanic hazards map, do some analysis on it to produce that map. So using the population of each county, I'm going to ask the program to shade or color code the counties based on population. So here is my state of Oregon based on the population. So the yellow areas are the least populated areas, and the red areas are the most populated areas. For your reference, this is where Portland is. That explains why it's so densely populated in this area. In addition, I've got these triangles that represent the location of volcanoes, and the size of the triangle is proportional to the number of eruptions that have happened in those volcanoes. So where are the largest volcanoes? In Deschutes County and Hood River County. Those are the two areas where you have the largest volcanoes. So just by doing this simple query of where are the most populated areas and where are the most frequently erupted volcanoes, we've produced a very simple tool to look at how planners should work. This is not something that a county would use to plan, but this is good enough for our understanding, to improve our understanding. Let's look at another example. In this case, we're going to look at the number of farms. Let's look at agricultural data. And I'm going to throw in the highways and the railroads and produce a agricultural transportation analysis map. So here what I've done is I've color-coded the towns. The darker green is where there are more farms. Sorry, I said towns, I'm sorry. Color-coded the counties by the number of farms. So Lake County has the least number of farms, falls into that 153 to 401 category. And the darker green is where you have more farms. Do you see a pattern in where the most densely, where the highways are most dense and where the railway road is as well? So the yellow lines represent the railroads. So these are railway lines, and these are your highways. So do you see a pattern? Is there a difference? Is it uniform or is there a difference?
Yeah, there's a difference. There's more railroad lines where there are greater numbers of farms.
Yeah, so the railroads, you don't have any railroads in this section of the state. No railroads in this section of the state. There is one that connects up to Umatilla, and then it goes out towards the west. But there's nothing in here, right? Similarly, the highways are more densely, there's a higher density of highways in this area. It must be said that it's also related to the population. It's not just the farm. But again, this is a very simple example, so we don't want to get into too much detail and clutter our understanding. Okay, so this is another example of a overlay, but we're looking, all the data sets are approximately the same time. They're not different time periods. We're trying to understand how these spatial relationships work and where different things are located, where different features are located. Let's get to our Colorado example. Now this is a very interesting example because this is an aerial photograph from 2023 contributed by, like I mentioned, Richard Hubler and Deacon Aspinwall. This is the location. From this corner, Calvillos is about 500 feet, just for your reference. And this image, this is the location of where the county found oil in boreholes. And they were very confused as to why there was oil. Why did they find oil in the boreholes? Deacon Aspinwall apparently found this surveyor map, which is from 1942. It's a very high resolution map. It's 1 inch is 200 feet. The standard topographic maps are 1 inch is 2,000 feet. So this is very detailed, and it's from 1942. And he had this idea of overlaying this map on the aerial photograph to see if he could figure out what was going on. Why was there contamination at that point? So they, Richard and Deacon, they georeferenced it. They georeferenced as in they added coordinate information to this layer so that it would plot at the right location, which is over the aerial photograph from 2023. And again, that's your 500 feet from Calvillos. That's the reference point. And this is the area that we were interested in. So let's just look at what is going on here in this area of the surveyor's map. So you'll notice that they were doing some kind of oil transfer here in 1942. And I'm assuming, that's what Richard and Deacon mentioned to me, that they're assuming that the oil that they found in the boreholes is probably left over from the activity that was happening at the time that the surveyor produced the maps. So this again is a overlay. If you notice, this is an overlay. You're overlaying data, but the layers are not the same time. They are different time periods. One is from 2023. The other one is from 1942. Okay, before we get to our last example, just wanted to throw this up on the board one last time about what GIS is, and I'm hoping that you are making these connections well at this point. And we are going to, I'm not going to spend any more time on this, I'm just going to go ahead and get into the last example, which is the Tennessee example for hydrology. So we're going to go to the northwestern corner of Tennessee, which is where the red dot is located at. This is Reelfoot Lake. A closer look at the lake. This is the lake, and you'll see that the Mississippi River is just next to it, and all these areas are where there's a lot of agriculture that's practiced all around the lake. The lake is very important from a recreational point of view. Lots of boating, fishing, hunting, etc. happens centered around the lake. People just, it's actually in the winter time, the bald eagle comes to, they spend some time at Reelfoot Lake. So people also come here for bird watching. Now the problem is, you'll notice that, incidentally, this section here is the Mississippi Bluff line. So that is, these are the hills, Mississippi hills. And in this area, you'll notice that these sections are pretty densely vegetated. However, there are some areas which are open. That's where they've cleared the land for agriculture and for pasture land. Now, these areas are more problematic from a clearing of land point of view because these areas are steeper. Steeper areas mean that if you have this steeper area, it would also mean that there's more erosion here. These are gullies that have formed. So this is your, maybe it's a pasture, maybe agricultural land. And these areas from where water is coming down can very easily, because it's sloping, can remove large sections of the sediment and create these deep indents. Now, where does all the sediment end up? Or just east of, just east of the bluff line, all of the sediment is ending up in the lake. So the lake is filling up. In fact, they had done a study in the early 90s where they had predicted that within about 200 years, the deepest parts of the lake would fill up. So the Tennessee Wildlife Resource Authority wanted to find out the rate of sedimentation that is happening in this area. I'm not going to get into the whole detail, all the details of the project. I'm going to present this in the fall, the entire project, but I'm just going to show you how you can map hydrology using GIS. So what we're going to do is we're going to go into this area. This is the Samburg area, and a closer look here. This is the town of Samburg. And you'll notice that this is an area where land has been cleared. And let's take a closer look. You can see these gullies here too. How deep and all this sediment is coming out and ending up in the lake. Okay, so let's start by going to, oh gosh, I'm sorry, this is cut off here. This is a section of a topographic map from 1925. And just let me go back one time here. This little creek that's coming into the lake or flowing into the lake is called Indian Creek. So we're going to work with just this Indian Creek for the rest of this section. So this is Indian Creek flowing into the lake. This is the town of Samburg. You can see the last two letters of the word Samburg, RG. And this is a map from 1925, a section of a map from 1925. Let's go to 1939, the next edition of the map. What difference do you see here? To the river, to Samburg, any other cultural features that are different? Yeah, absolutely. The town has grown. Anything else?
The little peninsula in 1925 seems to have disappeared. Or the sediment has come up to make it appear.
Yes.
Right,
Are you referring to this?
yeah.
Yes.
It looks like it's all filled in around.
Yeah. How about the channels? Is there a difference in the channels, Elijah?
The channel is from going to like curving left to being straight.
Okay, so you have this channel that's going towards the southwest. You still have that southwestern channel. It's slightly different from what it was earlier. And you've got this new channel that's going towards the northwest, right? Let's take a step forward and go to 56. What's happening in 56? Any changes to the channel? Let's give someone else a chance. Who else? Is there a difference in the channels?
You just have one, and it's moving toward the northwest, but away from town.
Yes. Yes, that's true. The town has grown, but it's also moving away from town. It's changed course slightly here too, right? If you go to 67, again, that channel has continued, and it's now created this land bridge. It's blocked up the section of the lake. Now, before we go forward, I'm going to show you a video to show you why these channels are shifting. What's happening? What is causing the channels to shift? So here is a video. Do we have to? That I made in our stream table. It needs to. Okay, so consider that this is the erosion in the bluff line where it's confined, the flow is confined, and it's carrying sediment. It's coming out to this spot here, which is open and it's gentler, the slope. And let's look at what begins to happen. It's pushing out the sediment into the open area, and you have this channel that's active at this point. It's still active, and now it is changing direction. Notice that it's now here, and this channel is now going to move over here. So over time, the channels are shifting. Why are they shifting? They're shifting because the channel itself is getting overwhelmed with sediment, and it's avulsing from one end to another. So that's why we see, that's what we see here. The topographic maps are showing us that the channels are shifting, and it's clear that the landmass has blocked up the lake as well, and the channels are shifting from one end to another. So this is the 67 image. Let's look at a more recent data set. Let's go to 2011. This is a LiDAR data set from 2011. What is the channel doing now? The channel is now going out in this direction, and there's one that's going towards the northwest. The paleo channel, which is this one here, is now completely overwhelmed with sediment, and it's just a pale remnant of itself from what we see here in 1967. So this is a LiDAR image. So what has happened in between 67 and 2011? When did this course change? We don't know because there are no more topographic maps, and there's no LiDAR data in between these two. So what do? We can use an aerial photograph from 1980 and see that this bend, because remember, our objective was to see when did this happen? When did it go towards the southwest? So we see that this shift happened at least in 1980. I'm not going to bore you with any more aerial photographs. We could add more and pin it down to a particular date, but this should give you an idea of how you could map channels using a combination of aerial photographs, newer LiDAR data, and topographic maps that can be used to identify the changes in the channel which are associated with deposition of sediment due to excess erosion in the uplands. So this is an example of where, in this case, I could use these different layers and then stack them one on top of the other to get the changes in the channel. So it would be still an overlay, but it would be a time series analysis of how the stream or this particular stream is shifting. Just to close this up, we did a calculation on how much sediment has deposited since 1925. There is, according to our calculations, there is a total of 300 million cubic feet of sediment that is deposited all along the eastern margin of the lake. So that's the amount of sediment that, according to the calculations that we've made. Okay, so now let's go back to what Dr. Benson said. What do you think? Do you think he was right, or was he just being funny? Definitely, because there is a lot of applications in GIS that you can use in different fields, because you can be a biologist or a sociologist or a geoscientist and use these skills to do analysis, right? So definitely it is a very an area where you can find employment very quickly. The science of where, hopefully these examples show you why the science of where is such an important definition for GIS. And again, we did create, analyze, and map some of the data. We didn't do very much analysis or manage the data too much. The data sets that I showed you, you can not know GIS and still use it. Or not bring it into GIS, for example, a topographic map or an aerial photograph. You don't need to know GIS to use those. You could put it under a stereoscope and look at get a three-dimensional image, or you could just look at a map in Google Earth and make some basic and do some basic analysis. The reason why I say this is I'll be teaching a 1-credit class in the fall that looks at all these different data resources. So please, if you are interested, I would recommend enrolling for that. So that's all that I have, except for I would like to open it up for questions, and that's my dog, Dushtu. Any questions?
What software are you using to analyze these maps?
ArcGIS Pro. And it's all it's programmed. The graphic the functions are in Python. They're all programmed in Python. Any other questions? I was actually loading my groceries in. That's why he knows that he needs to. Yeah. Any other questions?
So what's the price of the ArcGIS?
It's actually very expensive. Doug might know how much the licenses are.
I haven't priced the desktop versions recently. What a lot of people engage in that want to have operational functionality for GIS operations would, a lot of times you can get a membership in ArcGIS Online, which would then give you an access to an ArcGIS portal, which contains innumerable data sets and functionality that allows you to share data and tools and workflows with other people quite easily. So I think that's probably where people are trending to engage. As a personal user, it would probably be the most affordable way. But there are some open source, CardView, I believe, is a open source GIS software that's available to folks. And so there are other avenues that people can take.
QGIS is also free. QGIS, that's also free.
Yeah.
That's a free software package. But we've got the licenses through we've got an agreement with Colorado State, and we pay a very small amount of money for our licenses, and we've got unlimited licenses for our students. So all our computers in Porter Hall have ArcGIS Pro on them. And we have individual licenses to install on student computers as well. As long as they have a adams.edu account, or even faculty members can use it. Anything else? Thank you.